All right, in this technical reference, we're going to do a deep dive, and I mean a really focused dive, into the syntax of UML sequence diagrams. We're going to break down the notation piece by piece. The goal here is that by the end, you'll have a rock-solid, functional understanding. So let's jump right in. Okay, we're going to break this down into four main parts. First up, we'll cover the core components, the basic building blocks. Then, we'll get into the good stuff, how interactions are actually modeled. After that, we'll look at the syntax for control flow and logic. And finally, we'll wrap up with some of the more advanced notation for things like object lifecycles and a few other edge cases.
So take a look at this. This is a complete annotated sequence diagram, and it's going to be our main example. We're literally going to deconstruct every single piece of syntax you see on this diagram. By the time we're done, you'll know exactly what's going on here and how it's modeling this interaction.
All right, let's get into it. Section 1. Core components. These are, well, exactly what they sound like. They're the absolute foundation. Think of them as the canvas we're going to build our interaction on.
So the most basic thing on the whole diagram is the lifeline. It's just that vertical dashed line. And its one job is to represent a single participant, whether that's an object or an actor, and track its existence through the entire interaction.
Now, these participants really come in two main flavors. First, you've got actors. These are usually your users or maybe some external system that gets the ball rolling on an interaction. You'll see them shown as a stick figure or sometimes a stereotyped rectangle. And then, of course, you have the objects. These are your internal system components, and they're always shown as rectangles sitting right on top of their lifelines.
Okay, and this is where the notation gets really precise, which is important. The way you name an object follows a very specific structure. You've got an optional instance name, then maybe a selector in brackets if you need to pick one out of a collection, and finally, its class name, which always comes after a colon. Following the structure is absolutely key to making sure every single participant is clear and unique.
And here's the number one rule of sequence diagrams. If you remember nothing else, remember this: time flows down. The vertical axis is the timeline. Stuff at the top happens before stuff at the bottom. It's that simple, but it's the absolute key to reading the whole thing. Okay, moving on to section 2. Now we get to see how these components actually talk to each other. We're going to look at messages and activations. This is all about visualizing communication and showing when an object is actually busy doing work. Messages. This is really the heart of the interaction, and the key thing to look at is the arrowhead. It's a small detail, but it's crucial. A solid arrowhead means it's a synchronous message. So the sender waits for a response before it does anything else. On the other hand, an open arrowhead means it's asynchronous. The sender just fires it off and moves on immediately. Getting this distinction right is absolutely critical when you're modeling system behavior.
So what happens when an object gets one of those messages and starts to do some work? Well, we show that with an activation bar. It's that thin little rectangle you see on the lifeline. It visually marks the exact period of time when that object is active, executing a method and in control.
And this is a great example of what we call self-delegation. Check it out. When an object calls one of its own methods, you get a nested activation bar. See how the registration manager calls its own find course method? That creates that second, smaller activation bar stacked right on top of the first one. It's a really clear way to show recursive calls or any kind of internal method call. All right, next up, section 3, control flow. I mean, not every interaction is a straight line, right? To model anything more complex, we need a way to show logic, if statements, loops, that kind of thing. And that's exactly what combined fragments are for.
So a combined fragment is basically a box you draw around a part of the interaction, and you label it with an operator in the corner. This table here shows you the big ones. You've got opt for optional blocks, alt for alternatives, like an if-else, loop for, well, loops, and break to get out of a loop. Pretty straightforward.
Let's see how opt and alt work in practice. The opt fragment is for a single chunk of interaction that only runs if a certain condition, the guard, is true. It's basically an if-then. Then you have the alt fragment, which is for when you have two or more options. Each one has its own guard, and only one of them will run. This is how we model if-then-else logic, or even a switch statement.
And for iteration, it's pretty intuitive. We use the loop fragment. Everything inside that box just repeats as long as the loop's condition holds true. Now, if you need a way out, that's what the break fragment is for. It gives you an explicit exit. If the condition for the break is met, the sequence inside it executes, and then boom, the loop is done.
Okay, and that brings us to our final section, advanced notation. We're going to cover the syntax for an object's entire life cycle and then look at a couple of special message passing scenarios you might run into.
So objects don't always exist for the whole interaction, right? They can be created and destroyed. To show an object's creation, you draw a message arrow pointing right to the object's rectangle itself, and you label it with the create stereotype. And when it's destroyed, we mark that with a big X at the point where its lifeline ends. That X tells you exactly when that instance gets deallocated.
All right, a found message. This is what you use when you don't know or you just don't care who the sender is. Maybe it's an event from outside the system we're modeling. The syntax is simple. It's an arrow that starts from a solid black dot and points to a line. That black dot represents the unknown source.
And here's a perfect example of that. We've got a power surge event that triggers a circuit breaker. Do we know what caused the surge? Nope. Do we care? Not for this diagram. It's just some external event. Using a found message here is great because it lets us model how our system reacts without having to go and model the entire power grid.
Now, on the flip side of that, you've got the lost message. This is for a message that gets sent, but never actually arrives at its destination. It's super useful for modeling things like a network failure or a dropped packet. And notice the notation is just the reverse of a found message. The arrow points to a solid black circle, not from it. Take a look at this one. An email user sends out a spam email. See how the message arrow just ends at that black circle? That tells you the message is lost. It never reached anyone. This is a perfect way to model something getting caught by a spam filter or just getting dropped on the network before it could be delivered.
So, when you put it all together, you can model some pretty complex stuff. The key here is seeing how these elements combine. In this final diagram, notice the use of guard conditions, those checks inside the square brackets. They're controlling the flow. A register message only gets set if the found condition is true. If it's false, an error message gets sent instead. Now, as the note points out, this can get visually cluttered really fast. But the syntax gives us a formal, totally unambiguous way to model that logic. And that really leaves us with the big question we always have to ask in our own work. Where do we find that balance between being formally precise and keeping our diagrams clear and readable?